Hello, everybody. Mr. Hinnon here for probably the last application of uniform circular motion. Now we're going to look at vertical circles and the influence of them. So like we've been dealing with, and you had a problem on your homework, we've been talking about horizontal circles. So imagine like taking a lasso and swinging it over your head. Or if you had like one of those old time slingshots that you swung around and then let go. Or in our lab that we're doing, we're actually swinging something horizontally, so it stays in a horizontal plane above our head. This time we're actually going to be swinging something vertically around in a circle and looking at how the influence of gravity happens on it. So I'm going to start off with a question. What do you think would determine how fast you need to swing a bucket vertically so the water in the bucket will not fall out? So I've put a little link on here. I'm actually going to just jump straight to it because I think it's kind of a neat one. And it basically tells me that we can actually have a situation like this, where we actually have a bucket swinging around in a circle. I'm actually going to come over to this one. I've already got it set up. So this is the person from Flipping Physics, and he's going to fill this bucket with water, and we're just going to watch him as he's spinning around in a circle. And then he kind of goes through his normal flipping physics kind of. And if you've never watched it, it's kind of a silly one, but he has these three people, which are really him. So now he goes, there he goes spinning. That's what I mean by a vertical circle. So you have it in this particular situation, and the water stays in the bucket. It's kind of amazing. You can actually spin it around. Now we're going to try to make it as uniform as possible. He's trying to make it uniform, but you notice that kind of at the bottom, it tends to go a little bit faster. And then he's going to point out that, hey, if I just held it over, obviously the water falls out. So that's what we are dealing with in this particular example. So let's go back to our PowerPoint here. And if we were trying to look at what do you think would affect how fast you actually need to spin that bucket so that water does not fall out. Now, normally when I think of this, I would say everything, the masses of bucket, water, radius, and everything. But if you've kind of paid attention to my other notes on circular motion, you'll notice that the mass often cancels from the equation. So that'll be interesting to see if that's still the case. So if I just had to make a guess, an educated guess, I would guess it's not going to be the mass of the bucket or water, which means it's not going to be D or E, and it's probably just going to be the radius of the swing, which is kind of amazing that of those quantities, that would be the major factor. And I kind of think about it, if I had a longer swing, I would probably have to spin it faster to get it to go around in a circle and stay on there. So it'd be kind of, I suppose that makes sense to me. So to start off, we're going to be looking at this type of situation where we have some bicyclist or something going around in a circle, and we're going to look at the points on this vertical circle. So if I look at them, there's really 4 different points that are going to be important. The one that's at the bottom, that's point number 1. The sides, that's actually 2 and 4. And then the top, which is 3. So if I have this motorcycle come in and it goes through a curve around the circle, let's assume it just kind of continues to go around and around and around and then eventually kind of come out. The first one I'm going to look at is at the bottom. And if you notice what this picture is showing is a free body diagram. It's showing a dot to represent the object, and then it's showing all the forces that are acting on that object. And the reason why that's important is because if I have this object down here, the forces acting on it, the net force on it should equal the centripetal force. So the net force is equal to FC. So that's why I have mv squared over r here, which is FC on all of the right sides of this, because that's the net force. The centripetal force is not another force you add to it. It's actually the combination of the forces, and we need to have something towards the center. So if you notice, this force is larger than this force, showing that there is a net force towards the center. This force is toward the center. These are both towards the center. This is toward the center. We have to have something towards the center to cause it to go around the circle. Well, at the bottom, there's really two forces acting. We have gravity pulling it down, which is opposite from the direction, and then we have a normal force. In other words, the seat of it is going to push up, or the ground is going to push up. If you've ever been in the bottom of a loop on a roller coaster, you know the bottom of the loop on a roller coaster, you feel more pushed in your seat because the normal force on you has to be larger. A lot of times we take this equation for the bottom, and what we do is we rearrange it and we say, okay, the normal force at the bottom would have to equal, I'm just going to add this to the other side, it would equal the weight of the object, because it's got to balance that out, plus it would have the mv squared over r. And I'm going to put a 1 on here because they're saying that it could be a different speed, but we're going to stick with uniform circular motion. So we're going to assume that it's always going the same speed. So I don't really need a 1 or 2 and so forth. Now, if I wanted to, I could treat this as kind of my starting point, and I could look at the motorcycle, say, somewhere over here, and how that's going to relate it, and I could kind of relate it that way. Then you'd be talking about being up some kind of incline here, and one of the things that you would find is the angle here would be related to the angle of your incline. And you could relate that. Basically what would happen is the change, if I was talking about this point, is the normal force would actually equal mg cosine of theta plus my mass times velocity squared over r. And if you have the angle be 0, in other words, you're at the bottom, then the cosine of 0 is 1. And then as you bring it up, notice at the sides here, notice what happened to my equation. There is no mg part because it's perpendicular to it. So now since the normal force and the weight are perpendicular to each other, the angle would be 90 degrees, and you don't have any kind of mg or weight component to it. You don't have a perpendicular component, if you want to think of it, or a perpendicular component of your weight that's acting. So that's another piece we could do. We could actually generalize it this way if we wanted to. Just realize this angle would be the angle with the bottom. So straight down would be 0, and then to the side would be 90 degrees, and then we have 180, and then we would have 270. So 270 and 90, the cosine of those is actually equal to 0. What about at the top? Because the top is the next one that I think would be very interesting to kind of think about. So the top up here, the equation, notice that both the normal force and the weight are acting in the same direction. So if I were to bring this over, I would have the normal force would equal minus mg plus my mv squared over r. And what's usually important about this one is, again, what's happening is the cosine would be the cosine of 180 degrees, which is -1. That's why it's negative on there. And again, I'm going to kind of drop off that little 3. Let's just assume it's uniform, so the speed stays the same. So your normal force is actually smaller. They kind of show them as both being equal to the same, but there still has to be a component of it that's toward the center. The one that's the most interesting is, what is the point? What is the minimum speed needed to stay in the circle? Well, at the top, the key idea is that would be a point when all of a sudden your normal force drops to 0. In other words, you're not really pushed into your seat at all. You just kind of, you go around the top and you're just about to fall out of your seat. That's the best part on a roller coaster. You want to feel like you're about to fall out of your seat. You know you're not going to, but you want to feel like you're just about to do that. If that's the case, what happens is this goes to 0, and these two quantities actually equal each other. So the neatest equation is when you're at the top, that minimum V happens when mg is going to equal mv squared over r. Hey, do you remember how I said I bet the mass is going to cancel? That's exactly what's going to happen. So if you get your V equal to 0, obviously it's going to dump, but the mass of the water, the mass of the bucket doesn't actually matter how fast you are going. And so I can rearrange this, and the V would be the square root of just R times G. It looks very similar to our friction equation, but now we're talking about vertical circles. So the radius is the main factor. It's actually a square root relationship. So if you were to quadruple the radius, you would need to go twice as fast. But gravity is also going to be a factor. So if we are on different planets, those would affect it. So this is a good equation to know, as well as kind of this equation over here. They help us kind of figure things out. So let's start this one up. Let's say that you are going around, you have this aluminum rod and it breaks under a tension of 650 newtons. It's connected to a 12 kilogram spherical object. When the motor is turned on, the object moves in a vertical circle. We have the radius here. If the speed of the motor is continuously increased, what is the maximum speed the object can have at the bottom without braking? So in this case, we're going to be looking at the bottom equation. So this is going to be our Fn is going to equal the weight of the object plus mv squared over r. And I have the normal force. So this is the force of the aluminum rod. It's how much it's applying. That has to be 650. We don't want it to be larger than that. We know it's a 12 kilogram object. So this is actually going to be important to finding this out. Plus, I would have 12 times v squared over my radius, which is 6. Hey, that's kind of nice. So this is going to just basically cancel out and give me 2. So I have to just solve this. I'm going to bring this 12 times 9.8. So that's going to be somewhere around 120 something, and then bring that over to the other side and then solve for that V. We should be able to kind of calculate this out. So to kind of finish this out, let's see. I'm going to stop in the show, but I'm going to keep my ink so I can bring up my calculator here. So kind of looking at that, I'm going to have 12 times 9.8. That's going to give me 117.6. So the first thing that aluminum rod has to support is that. So what I'm going to do is I'm going to add that to my 650. Sorry for the extra noise. We have the dog and kids coming home. And then I'm going to divide it by 2, because that's the 2 happening right here. And then I'm going to square root that. And I get a 16.3. So this thing needs to be, the maximum speed it could have at the bottom is 16 meters per second. And so when I figure that out, it looks like C is going to be my best answer. So just a couple little equations that are kind of nice. I would probably add that little cosine theta part. I think it gives you a more general equation and you're good to go. Have a wonderful day.